Now we're going to look at two businesses and see how they make decisions in order to help them maximize profits using this technique that we call linear programming.
Chocolatier Bوريي is one of many chocolate factories in Belgium. All the chocolates produced here are created by hand using fresh ingredients. This makes their chocolates more costly to produce than machine-made chocolates.
What makes the quality difference is also the filling that we use in our candies. We use good butter, cream, eggs, no preservatives. We have here orange peel. It's a specialty sugared orange peel. We still sugar our orange peel ourselves, as you can see.
Yeah.
And this takes for about 3 or 4 weeks. This is no preservatives, the old-fashioned way of conserving fruit, and that gives it a very high cost. But this is the only way you can say this is quality.
Yeah.
The price is also, of course, higher.
Sure.
Let's assume that they'd like to increase production by making some chocolates by machine and some by hand. What's the best amount to produce of each type? In other words, how do they make sure that the amounts of each sort that they make are optimal? They cannot simply make any amount they choose because they're constrained in all kinds of ways.
It's very difficult now to find people in very specialized trained people for a long time commitment.
Let's assume the following constraints. Let's assume that there are 36 people who work in the factory and they work a 36-hour week. That represents a maximum of 1,296 hours of labour time each week. Overtime is clearly possible, but it's very expensive, so the company doesn't regard this as a meaningful option. They have 1,824 hours of machine time each week, and a batch of handmade chocolates requires 18 hours of labour time and 6 hours of machine time. A batch of machine-made chocolates requires only 4 hours of labour time, but 12 hours of machine time. Chocolatier Bوريي wishes to use its labour and machines as much as possible. Furthermore, the deluxe handmade chocolates make €89 a batch in profit, but the standard chocolates make only €55 a batch profit. Now, what does the mathematics of linear programming tell us about the best way for the chocolatier to organise production so as to maximise profits? Now, there are 7 steps, but we'll focus for a time on just the first 5. And these are: first, identify the unknowns and label them in some way, X and Y or whatever. Second, write down an expression for the objective function, the thing you wish to maximise or minimise, and express it in terms of X and Y. In this case, we've got something to maximise, profit. Other times it might be something to minimise, such as the cost of doing something. Third, write down all constraints on the variables X and Y. Fourth, write down any obvious constraints, such as which you may have forgotten about. Often these are non-negativity constraints. Here, for example, the output of batches of chocolate can't be less than 0. And fifth, graph the constraints in order to find the feasible area, that is, all the options that are possible. Just what choices does our chocolate manufacturer have that he can consider? So let's work through these 5 steps. Then afterwards, we can see how to finish the problem by picking the best combination of chocolate batches for maximising profits. Here we follow a series of steps in linear programming to determine how a Belgian chocolate producer should allocate his resources to maximise profits. In this case, we want to find the optimum number of batches of machine-made chocolates that we'll call M, and handmade chocolates that we'll call H. Now, since a batch of M makes €55 profit, and a batch of H makes €89 profit, our objective function can be written as maximise 55M plus 89H. But he has to do this within a series of constraints. First, there's a labour constraint. The handmade chocolates, H, needs 18 hours for each batch, and M needs 4 hours for each batch. And the total hours available is 1296. So the constraint is 4M plus 18H is equal to or less than 1296. We also have a machine time constraint. Each batch of M needs 12 machine hours, and each batch of H needs 6, and the number of machines available limits us to a total of 1824 hours. So our machine time constraint is 12M plus 6H has to be equal to or less than 1824. But there are also some non-negativity constraints. Batches of each type can't be less than 0, so we also require that H is equal to or greater than 0, and M is equal to or greater than 0. We now have an objective function, and we know what the constraints are within which we have to operate. So we now have a problem in a form which is soluble. So we've now established what is possible and what is not. Well, we said there were 7 steps, and we followed the first 5. Now let's do the other 2. And they are these. Number 6, we'll discover that the optimum is one of the intersection points in the feasible area. We need to evaluate these to solve for the maximum or minimum. In this place, we'll be looking for a maximum, that is, maximum profit. And 7th, our last step, will be to check that the final answer makes sense as a solution to the original problem. Are we sure that there isn't some other combination of chocolates that would make more profit while still meeting the constraint? We'll begin by graphing the constraints. The first constraint is the labour constraint. Now this is an equation of a straight line, so we can find 2 pairs of coordinates. So if we set M equal to 0, we get 18H equals 1296. So H is 72. So that's one point on the diagram. M equals 0, H equals 72. Now if we set H equal to 0, we have established a second point, and we can simply draw those 2 points. Now we've shaded the area to the right and above the line to show that those combinations aren't feasible for our chocolate producer. They're not within the labour constraint. Now let's add the second constraint. This is the capital constraint, the amount of machine time. And we can plot that in the same way as we did for the labour constraint. The constraint here is 12M plus 6H equals 1824. So if we now set M equal to 0, we get 6H equals 1824. So H is equal to 304. Now we find our other set of coordinates by setting H equal to 0. This will give us 12M equals 1824. So M equals 152. So from these pairs of coordinates, we've plotted the second line on the diagram, again shading the area above and to the right of the line to indicate that these are areas of non-feasibility. Now we need to add the non-negativity constraints. We've shaded the areas where H or M would be less than 0. And that means we've now established the feasible region A, B, C, D. So the possible levels of output meeting all of the constraints are within this box. So we can look at points A, B, C, and D. Point A has the coordinates 0 and 72. Point B has coordinates of 130.5 and 43. Point C has coordinates of 152 and 0. And point D has coordinates of 0 and 0. It may not be at all obvious how we got point B. Well, we use the principles that we've met before. We're finding the solution of a pair of simultaneous equations. So if we look at the two constraints, we have 4m plus 18h equals 1296. We can call that equation 1 our labour constraint. We also know that 12m plus 6h equals 1824. So how could we do that? Well, one way of doing it is to take our first equation and multiply it by 3. So that gives us 12m plus 54h equals 3888. Now we can subtract equation 2 from equation 3 to get 48h equals 2064. That is to say, h is equal to 43. That gives us one coordinate. Now it's easy to get the other one. 4m plus 18h equals 1296. And we've just established that h equals 43. So we can now write 4m plus 18 times 43 equals 1296. So 4m equals 522. M equals 130.5. So that's how we knew the coordinates for point B. We can now check on the 4 points which define the boundaries of the feasible region and see which is the most profitable for our chocolate producer. If we look at point A, if we produce at point A, then we produce no M and 72H. So our profits will be 55, the profits on an M, times 0, because we're not making any M if we choose this point, plus 89, the profits from a batch of H, times 72, the number of batches of H that we would then make, which gives us 6,408 euros as the profit which we would make if we chose point A. We could now perform the same task for points B, C, and D, and for point B, the profits are 11004.5, for point C, 8360, and for point D, 0. So we've established that point B represents the maximum profit. We know now how many batches of M and how many batches of H to produce in order to maximize our profits within those constraints. So when a producer has to maximize profits subject to a set of constraints, linear program is the only realistic way of establishing how to handle those resources in an optimal way.